Welcome to Math 31. This is a review of sigma notation, lesson 4. So we're going to look at a few earlier math topics that you would have covered in mostly Math 30 Pure. And we're then going to take these things, although they're not really essential for the unit we're in, but we do use them to help develop some of the area issues that we're going to run into shortly. So we use them and then we sort of discard them. Now you might remember from earlier days that the sigma notation looks like this, where you have down below this sigma symbol, the Greek symbol, you have I equal k. Now this represents the lower limit, and this represents the upper limit. And then this really is equal just to the sum of terms from that lower limit from I equal from k all the way up to n. So you add them all together according to a formula like f at I. Now, very useful when people see formulas because they tell the world that you're supposed to add all these things together. So they're just really a shortcut way to express repeated addition that adheres to a specific formula. So it's a compact way to deal with that. Now, here's an example. The sum of these terms from I is equal to 1 to I equal 3, and using the formula 3i squared minus 1. So what we do is, starting at the lower limit, we plug in I equal 1 to the formula. So it's 3 times 1 squared minus 1. And then the next one is 3 times 2 squared minus 1, and then plus 3 times 3 squared minus 1. And then we deal with all this, and this becomes 3 minus 1 is 2. Next one is 3 times 4. 2 squared is 4 times 3 is 12, minus 1 is 11. And then the next one, 3 squared is 9 times 3, 27 minus 1, 26. So we add these together, 13 plus 26 is equal to 39. So this whole thing is equal to 39, and so on. Now obviously this is a problem if you have many, many terms, or if you have a really complicated formula. In 30 Pure, you do develop ways to deal with certain ones like this. Now, the properties of sigma notation there's many of them, and I'm going to highlight a few critical ones. If you are adding two terms or two formulas together, f plus g, you can break it up. So it would mean that if you had, 2x squared plus x, this is equal to 2x squared plus x, if you wanted to. And in that case, it wouldn't make any difference what the lower and upper limit were as long as you were consistent with them. Now the next one is where you have a constant term. So c times the formula, you can actually take that outside the sigma. So if you even take a look at the one above, like 2x squared from whatever to whatever is equal to 2 multiplied by the sigma summation of x squared. If you wanted to, you could do that. Number 3, this is an interesting one because it's just the sigma set up with a constant. So for example, if you had 5 from, let's say, I equal 1 to I is equal to 3. Now there's nothing to substitute in. So your first term is 5, your second term is 5, your third term is 5. So you just add them together, or go 5 times 3. So you get 15 in either case. And that's what it's telling you. It's because the number's not changing. It's really just multiplication, the number of terms multiplied by the term itself. Now, the next set of properties is a little bit more complicated. You might remember this one from 10 Pure, even though that's they don't use sigma notation always in that course. But this is the sum of an arithmetic series, n times n plus 1 over 2. And it's an interesting formula. It's really just the sum of natural numbers. So 1 plus 2 plus 3 plus etc. like that all the way up for whatever, how many you ever want to add together. Now, the story with this one is that, I forget the name of the young mathematician years ago who came up with this, but he's sitting in class, or so the legend goes. Teacher says, what is the sum of all the numbers from 1 to 100, all the natural numbers from 1 to 100? And of course, this is not an easy question. Even now with calculators, it's a bit of a problem. But with no calculators, it's the sort of question that's supposed to take a while. So he had the answer in a few seconds. And what he did was he took, starting below, this is a smart kid, he worked his way down underneath it. And so he recognized that by introducing that downward descending sequence, that you can add these together. The pair, 1 plus 100 is 101. And every one of those little pairs adds up to 101. And you've got 100 such pairs. And then you divide by 2. And you'll see that that actually corresponds. You have to divide by 2 because you have doubled it by introducing the descending one sequence. And you see that that matches. In this case, n is 100 times 100 plus 1, and then divide by 2. So an interesting formula. We probably won't use it ourselves too much in the next little while. Number 5 goes like this. A little more complicated, but this is for I squared. And this formula we will work with in the next lesson. And then we discard the whole thing, but it comes in handy in those rare occasions. So n times n plus 1 times 2n plus 1 over 6. So this would be, for example, if you did need to evaluate, let's say, the sum of I equal 1 to 5 of I squared. Now this one you can Armstrong your way through because it just means that you're starting at 1. You go 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Now check that all out, but you'll get 55. Now that's one way to do it. But using this formula, you just recognize, okay, n is 5, your upper limit, multiplied by 5 plus 1 is 6, multiplied again by 2 times n plus 1, so 2 times 5 is 10, plus 1, 11, all divided by 6. And this will give you 55. Same thing. So for more complicated scenarios, that's probably the way you want to do it. Number 6 is for I cubed. Not likely that we're going to use this one again, but you never know. You might decide on your own that you find that helpful. N squared times n plus 1 squared over 4. It's supposed to work. I almost never use this one. In fact, I don't even remember it if I didn't have it written in front of me. So that's it for this lesson, a short little review on these topics, and then the next lesson is going to launch into what they call the area problem. So this is where things get interesting, and this is where we can apply at least a few little bits of the sigma work into it. Thank you for your time.